Usage of harmonic number and polylogarithm might make this integral easier. Yeah. So while doing integrals, like rather than going straight forward, like most of the time it's like helpful to go straight forward. Yeah. But there are really powerful tools like harmonic numbers, harmonic sums, and polylogarithms, like that are like too powerful. And while if we use them, like it simplifies the integrals a lot. There are such cases, and one of them is this one as well. So what happens is, let's say if we while doing the integrals, like if we are trying to introduce harmonic series, and let's say we come across the series like Hn x to the power n, where x can be anything, then we already know that this is just minus ln of 1 minus x by 1 minus x. Yeah. Or let's say if we have the generalized sum, and here n goes from 1 to infinity. Let's say we have n equals to 1 to infinity and Hn of order p. We also know this. We know like all lot of different facts that can be helpful. So we can use these tools because we have researched a lot on those tools, and we can now use it proudly. So let's say, even though let's say we have some other, we come across some other like ideas. Let's say n back to the power n. We also know this. So since basically the idea is, since we know a lot of these formulas directly, so that can be helpful. Now this is, we can just divide by x and integrate this expression. Yeah. And that gives us li2 of x plus 1 by 2 log square 1 minus x. Similarly, we also have other expressions like classical Euler sums. Yeah. This is like if we have sum from n equals to 1 to infinity of Hn by n to the power q, we already know that this is 1 plus q by 2 Riemann zeta of n plus 1 minus 1 by 2. Yeah. And then sum from k equals to 1 to q minus 2 Riemann zeta of k plus 1 Riemann zeta of q minus k. Yeah, we also know this. Since like many people have derived these ideas for us, and now it will be easier. We are too powerful. And also if you like try to go to the polar logarithms, there are ideas like if you like come across li2 of 1 minus x, you can easily write this as Riemann zeta of 2 minus log x log 1 minus x and then minus li2 of x. Now it goes in terms of li2 of x, and these will be integrable. Yeah. So basically what I was saying is, since we have a lot of identities already proved for this, it will be easier to go to harmonic numbers. Yeah. So now for this case also, what we can do is, we know that here is an identity involving log square 1 minus x. So we will try to use this. Yeah. And we will see how easier it will be. So integral from 0 to 1 log x by x, and log square 1 minus x is just 2 times sum from n equals to 1 to infinity Hn by n x to the power n minus li2 of x. Yeah, this is the thing. Okay, no, here also this should be 2. Okay, now that's the thing. And what can we do after this? We can basically separate this into two integrals. So let's say 2 times sum from n equals to 1 to infinity, integral from 0 to 1 Hn x to the power n minus 1 log x. Yeah. And then by x. Is it? Hn x to the power n minus 1 log x. Not x. Sorry for this. By n. Yeah. And then dx. And similarly, over here minus 2 integral from 0 to 1 log x li2 of x by x dx. First of all, let's check if this is correct or not. Hn x to the power n minus 1 by n log x, 2 is there, fine. And over here 2 integral, again fine. Now what we can do is, while doing integrals, as n by n is just constant, so we can integrate this part, and this is just a special case of beta gamma function, so we can use the beta gamma function now. Sum from n equals to 1 to infinity, we have hn by n, and this is just, we know that if log x has power n, this is minus 1 to the power n, and then gamma of n plus 1 2 by this plus 1 is n square. Yeah, and then over here what we can do, minus 2, we can use integration by parts. Yeah, log x, and this thing is li3 of x, and then minus integral from 0 to 1 by x, li3 of x, so li3 of x by x dx, isn't it? Now over here, this is just minus 2 times sum from n equals to 1 to infinity of hn by n cube, and this can be evaluated from the classical Euler sum, isn't it? Yeah, and for this one we have minus 2. Okay, so this is from 0 to 1. We have log 1 li3 of 1, that's 0 because log 1 is 0, and again it's for the second one, li3 of 0 is 0, but this one is minus infinity. You can use limits and use the sum expansion and then L'Hopital's rule, and through the limit x goes to 0, you get that this to be 0. So 0 minus 0 basically, and this one now is li4 of 1. Yeah, using the property of li function. And now to evaluate this, we can use the classical Euler sum, this formula. Yeah, if you put q equals to 3 over here, you get 1 plus 3 by 2 zeta 4 minus, from k equals to 1 to 1 itself, 1 by 2, and then this is zeta of 2, zeta of 3 minus 1 is 2. So what do we get? 5 by 2 times, this is pi to the power 4 by 90, minus 1 by 2, this is now pi to the power 4 by 36. Yeah, so what do you get? Pi to the power 4 by 36 minus pi to the power 4 by 72, that is pi to the power 4 by 72. Yeah, so what do you get now? Basically minus 2 times pi to the power 4 by 72 plus 2 times pi to the power 4 by 90. Yeah, that's basically minus pi to the power 4 by 36 plus pi to the power 4 by 45. If you take LCM, that will basically be 180, and 36 times 5 is 180, minus 5 pi to the power 4, 45 times 4 is 180, so 4 pi to the power 4, and that gives us minus pi to the power 4 by 180. That's the answer. So basically for this one, like, our tools were too powerful to deal with this one. Like we already have a lot of tools that these sums can be easily evaluated. Also li2 of x by x can be easily evaluated. Yeah, and yeah, we also have beta gamma function for this one. Yeah, so we already have so like great tools that this just become a piece of cake. Yeah, and this wasn't too hard. If we have to talk about the flow, first of all, I shared with you about like how there are such tools involving harmonic numbers and polylogarithms, and then I just tried to show you that there's also one involving log x 1 minus x. So I substitute log x 1 minus x with its corresponding value, and then we had two different integrals, one with beta gamma function. After building beta gamma function, this went into classical Euler sum. This was easily simplified with polylogarithm, and then we got some expressions for pi, we added them, and we got the answer. That was it. Hope you enjoyed the video. Thanks for watching. Look forward to seeing you in the upcoming videos too.